This is Felix the cat. If Felix is chasing a laser along a straight path with a constant speed, or if he is jumping up vertically to catch a string, he is exemplifying 1D motion, the first being in the horizontal x direction, and the second in the vertical y direction. In the first example, Felix is experiencing a change in position in the x direction, which can be characterized by either displacement, which is his final minus his initial position, or distance, d, which is his total distance traveled over his time. The cat is also traveling at a constant velocity. Velocity is measured by the change in position over the change in time. Since his velocity is constant for this motion, we can assume that average velocity is the same as instantaneous velocity, which is the derivative of a position graph at any point of time. A particle's motion with a constant velocity can be. The following are position, velocity, and acceleration versus time graphs for motion with constant speed. The first graph is position versus time, and as you can see, as time increases, so does this object's position. The second graph is velocity versus time, and you can see that the object has a positive constant velocity throughout its movement. And the third graph is showing that the object, or the cat, has a zero acceleration, no acceleration at all, for his motion with constant velocity in the positive x direction. The second example of Felix's motion is an example of free fall motion. In this example, we are going to assume that he moves straight up and down when jumping to get the string, and that there is no air resistance. Felix's position change in the y direction will be modeled under constant acceleration due to the gravitational constant g, which is negative 9.8 meters per second squared. A particle's average acceleration can be calculated by taking the change in velocity over its change in time, and its instantaneous acceleration is just the derivative of the velocity at a certain time. Due to acceleration, Felix will not have a constant velocity in his jump for the string. If his acceleration is in the same direction as his motion, he will speed up, and if his acceleration is in opposite directions, he will have a decrease in speed. Because acceleration due to gravity is downward and Felix is initially jumping with a velocity upward, he will experience a decrease in speed on his way up to get the string. But on his way down from the string, once he starts with the initial velocity of 0, he has an increasing velocity because he is traveling along with the acceleration in the same direction as the acceleration vector. This shows position, velocity, and acceleration versus time graphs for motion with constant negative acceleration, or the previous example, free fall motion. The first graph is of position versus time. As you can see, initially, position increases more rapidly over time than further on in time due to the negative acceleration. The second graph is velocity versus time. As you can see, there's a decreasing velocity over time. And the third graph is showing that there is a constant negative acceleration throughout time. I did problem 29 from the book. Problem says, Felix is moving with uniform acceleration and velocity of 12 centimeters per second in the positive x direction, starting at x equals 3 centimeters. If x coordinate 2 seconds later is negative 5 centimeters. What is the acceleration? And I started this problem by first declaring that at t equals 0 seconds, Felix is at position x equals 3 centimeters, and at t equals 2 seconds, Felix is at position x equals negative 5 centimeters. We are also given that the initial velocity is 12 centimeters per second squared. From this information given, we can use the equation for final position to solve for the acceleration by plugging in x final to be negative 5 centimeters, x initial to be 3 centimeters, velocity initial to be 12 centimeters, and time in both positions to be 2 seconds. From this, we solve that acceleration is negative 16 centimeters per second squared.